Thank you very much. So today I would like to present key speech by topic of generation of extreme ultraviolet vector vortex beams in laser-induced plasmas and gases. So I'm presenting this presentation also in behalf of Rashid Ganeev, and of course there are a lot of results obtained together with our Latvian colleagues, with our German colleagues. So at the end of this presentation, I will speak a little bit about. So let's start. So this is outline of presentation. So it consists of three parts. Actually, quite extended introduction. Then I will present some very interesting experimental results, and at the end, some conclusion work and something like that. So let's start. So topic of my presentation, it is consists of many parts. So we will speak about vector vortex optical beams. We will need something called ultrashort laser pulses. And third part, it is laser-induced plasma as media for interactions. And the fourth part, so is the main topic. It is the high-order harmonic generation. So actually, it is what by using of this process, we obtain this XUV extreme ultraviolet beams. So let's start from vector vortex beam. So I'm sure later today, Dr. Naresh Reddy will make a much better presentation about this topic. Just in short words, for example, here on this slide, you see a cross section of beam, of vector beam. So what is so special with this beam? So the special here that first of all, it has singularity in the center of the beam. And so what is the origin of this singularity? So it's very simple. So on the top picture, you see it is radial polarization distribution. So we're all familiar with linearly polarized beams. So it is usually what you get from the any laser system. Also, if you use something called a quarter wave plate, you can convert this linear polarized beam to circle polarized. But here, using so-called S plate, you can obtain a very special radial distribution. So in this case, it is radial. So all polarization vectors, they directed from the center to the edge of the beam. It is kind of sunlight from the center. So, and that's why in the center we have singularity, because if we continue these lines towards the center, so in the center we will have polarization state with direction at all sides at the same moment. So it is of course impossible. That's why we have a singularity. Another state of polarization, it is azimuthal polarization distribution. So vectors of polarization, they form circles from the center to the edge again and again. In the center, we will have singularity, because otherwise we will have again undefined polarization direction or something like that. So this is vector beam. So you now nowadays you can get them very easily. So there are specially prepared optical elements. They called S plate. So they're prepared for definite wavelength. So also okay. Let me continue. So okay, and this is just a small demonstration of real measurement with this kind of S-wave plate. So first of all, if you combine S-wave plate plus linearly polarized light, so you get vector beam. So, and depending on the orientation of S plate, you can get radial or azimuthal, and you can easily check what is the current state of polarization in your beam. So just using any analyzer. So in this case, it was a simple Glenn-Taylor prism, and we recorded light passing through S plate through Glenn-Taylor, and here, so here we because the transmittance for Glenn-Taylor depending on orientation of polarization vector. So in this case, we observe this kind of picture. In case of azimuthal, we observe this kind of picture. So I think it's quite clear, and it is primarily connected with the previous slide. Okay. Okay. So another interesting feature of S-plate. So if you combine circular polarized light, you will get another type of singular optics, singular beams. It is called vortex beam. So a bit explanation about what is it, vortex beam. So vortex beam, it is something with the helical wavefront. So you remember the wavefront, it is just surface where you have the same phase. So in case of so in the most common type, it is Gaussian beam, where so it is designated here. So you have like Gaussian distribution of intensity. Also wavefront also have Gaussian shape. But in case of vortex beams, there are additional degree of freedom. It's called topological charge. And wavefront is formed in the shape of twisted in shape of twist, and topological charge defines how many twists you have on the length of single optical cycle. So in case if you have topological charge equal to 1, so there will be one twist during optical cycle. In case of 2, it will be 2 twists, and so on. So also it has sign, so it can be positive or negative depending on in what direction its helical wavefront is. So this is vortex beam. So and returning back to here, so if you combine circular polarized light with vortex with SOS plate, so you will get vortex. And here you can so again we using the same setup, just quarter wave plate, S plate. So, but in this case, of course, after quarter wave plate, it will be circular polarized light, and you can absorb part of this helical wavefront. So it's very interesting picture. Otherwise, okay. Okay, so why it is so important to work with this kind of singular beams? Because actually they can be used for many applications, with communication systems, laser material processing, and so on. So here it is a very simple demonstration. So we work together with the Institute of Astronomy, and we just tried to improve a laser ranging LiDAR system. So why it is required? Because they're using this Cassegrain telescopic system here. So, and of course, in the center, there are this dark blind spots. So very simple, it was very simple idea because transmitters for S-wave plate is very high. It actually reach up to 95% if you're using the S plate, design it exactly for precise wavelength. So you can really increase transmittance, you can really increase returning rate of photons from the satellite. And so it is just a simple demonstration where this vector and vortex beams can be used. Okay, so let's return back. So remember second part, it is something called ultra-short laser pulses. So here it is just demonstration of one of the one of the system, this kind of system. So in this case, it is demonstration of fiber-based femtosecond laser machine. It's really impressive. So by itself, obtaining short pulses, it is separate and complicated task. So it is just schematic representation of one approach, how you can get high repetition rate microsecond pulses. So in this case, it is a fiber-based machine. So here we have oscillator as usually, then we stretch, then we amplify to stage amplification. So the most important that at the end, So after compression through hollow core fiber system, so you can get a very short laser pulse. So so of course this wavelength range could be different, could be quite broad, but for typical systems, it's like for Titan Safari system, it is starting from 780 nanometers to 820. So in case if you're using NDX system, it could be 1064. If you're using fiber system, it could be 1500 nanometers, something like that. And here, so once we have ultra short pulse, so ultra short, it means the duration of this pulse is measured in tenths of femtoseconds. So actually, right now, you can work with systems with so-called Q cycle laser system, where you're generating laser pulses with the duration of few optical cycles. It is like 5, 8 femtoseconds, something like this. So femtosecond is 10 minus 15 degree of second. So, and here it is just some characteristics for very typical femtosecond machine. So, for typical femtosecond machine, energy will be around 5 millijoules. So, energy per photon, so this one for in this range, it will be from 1 to 1.5 electron volts. So, and pulse duration around 30, 40 femtoseconds. So, but if you but once you focus this kind of laser pulse in the spot with the sizes around 100 plus micrometers, the diameter around 100 plus micrometers, so you can easily obtain intensities in 1015, 10 in power 16 watt per square centimeter. So just for comparison, these are information about current electrical generation capacity, about instant power of United States electrical generation capacity. It is information by 2023. So it equal 1.2 in 10. So only 12 in power of 12. So you see by tabletop femtosecond laser system, you can easily generate pulse with instant intensity like three orders higher than whole electrical generated capacity of United States. But of course, we're talking about very short period, so we reach this intensity at a period of time like this, 30, 40 femtosecond, and it's very located and very limited space where you focus your laser beam. So in this 100 micrometer spot, so but in this 100 micrometer, you really have something really high intensity, and you can study strong field processes. And so on. So let's continue. Okay. So now let's go to the third part of introduction. Let's start speaking about laser-induced plasma, why we would like to use this plasma. So here it is a very simple schematic. So usually we generate, so we're using so-called target chamber. So it is vacuum chamber. You place your solid state target inside the target chamber. Then you use part of maybe initial beam or part of uncompressed beam from femtosecond laser system. And you focus inside chamber and you generate laser induced plasma plume. So why we would like to use this laser induced plasma as target for ourselves? So so laser induced plasma plumes lifetime of this object is actually very short. It is a few hundred nanoseconds. So of course it lasts longer, like up to tens of microseconds, but there are very short periods where the plasma plume is very dense, and it could be used as effective media for high order harmonic generation, for upconversion of fundamental laser wavelength. So laser induced plasma is very unstable. So let's say it is not stable object. So it changes very fastly. So here it is just some presentation. We try to calculate what is the speed of spreading of plasma plume. So as you can see, so overall result, it is like 10 in power, it is thousands or tens of thousands kilometers per second, actually. So plasma plume is a very fast object. Also, plasma plume change its own condition, own state. So from point of view of temperature of plasma, from point of view of content of neutral and ionized entities inside plasma. So, laser-induced plasma is not simple task, but another opportunity. So we can control geometrical characteristics of plasma. So we can use not only one plume, but we can generate so-called structured plasma if we use some multi-slit mask, for example, and focus enough intense laser pulse, so we can generate multi-plume plasma, multi-structured plasma, so we can generate extended plasma. So why we would like to use laser plasma? So yeah, it is a very hard target. It is hard to use, but you remember that actually our probe, this, so we're using ultra short laser pulse as probe for this media. So but pulse duration for this probe is very short. It is 30, 40 femtosecond. So from point of view of our probe, this laser-induced plasma plume actually is very slow. So we have plenty of time to direct, to combine, to study states, to study plasma media at any moment during evolution of plasma plume. So by choosing correct time at evolution line of plasma plume, actually we can control both conditions of media, density of media, number of charged ionized entities in particles in media, and so on. So actually, this is the reason why we would like to use plasma as a source of XUV coherent radiation. So okay, now we have vortex vector beam. Now we have ultra short pulses. Now we have media for to study. It is laser reduced plasma. So let's combine everything. So and once we combine, so of course, we need to synchronize to moment when we ignite when we excite plasma plume. Then it should be combined exactly with the moment when we probe with the femtosecond pulse. But if we successfully resolve all these issues, then we will get high order harmonic generation from plasma, from gas media, and so on. So in case of jets, of course, there is no need for synchronization. And this is how it looks like. So for high order harmonic generation, we're using both target chamber and XUV spectrometer in very high vacuum condition. So and then after interaction, yeah. So our beam containing high order harmonics, it's spreading to XUV spectrometer. Then it is dispersed by flat field grating system, flat field grating, and we can absorb using intrachannel plates spectra of harmonic speed. So this is so this was converted from fundamental radiation with the wavelength 800 nanometer. So and here we can absorb part of the spectra. It is from 9th harmonic up to 17th harmonic. Okay. So however, the harmonic generation it is very good example of non-perturbative phenomena. So there is no, so we cannot analyze it using perturbation method, for example. So it is strictly non-perturbative phenomena. So there is no dependency. So this kind of dependency usually you can observe for perturbative phenomena. So there is no dependency. So you have to so also calculations and modeling of this kind of interaction also is very challenging task. So here it is just some example. So okay. So and why we talking about this high order harmonic generation in plasma and gases? So you know that it is very crucial right now to obtain new sources of XUV radiation because this radiation is used for first of all, for production of different microchips. For example, this CPU, central processing units, it is actually a product uh, interaction of ultraviolet sources with by different methods. So it's united by name of lithography. So by method of lithography, you can obtain this central processing unit, other microchips. And this is really a huge race between East and West right now. So China is looking for new sources. And still, higher the harmonic generation, despite some problems with the conversion efficiency, it still could be the source for extreme deep ultraviolet radiation, and this radiation later can be used for purposes of microelectronics, lithography, nanolithography, and so on. And there are methods how you can improve signal. So we can use high repetition rate lasers together with the rotating targets. For example, this is example of how the stable harmonic generation from aluminum rod. So it was rotated inside target chamber, and we used kilohertz class femtosecond laser system, and we obtained a stable source of harmonics within 1,200 seconds. So I think it's 20 minutes. Okay, now let's go directly to our results. So I'm sorry, maybe we'll take a bit more time for presentation. So now we combine our vortex vectors beams with high order harmonic generation. So here it is just representation of our experimental conditions. So we using linearly polarized, circle polarized light. Then we combine this light with the S plate or spiral phase plates to obtain vortex beams. And as a result, for probe, we probe our target. So in this case, it was gas jet, argon gas jet. So we probe it with radially polarized beams, with azimutally polarized beam. Also, we probe it with vortex beams, but vortex beam with wavefront with linearly polarized with polarization, linearly polarized light and circular. Okay, let's go to results. So it is overall result. So the result was published in ACS Photonics in 2023. I will try to explain this experimental result one by one. So let's start from the beginning. So we're using vector vortex beam. So, but also we use second harmonic generation from this beam. So why we would like to use it? So when we worked in, so this result we obtained it in Münster, Germany. So together with in close cooperation with the team of Professor Kevin Zaharia and his team and his lab. Unfortunately, we had some problems with the maximum energy of femtosecond laser. But we resolved this problem. So we used so-called two-color pump. So we inserted additionally second harmonic, and we generated very small. So actually, it was even smaller. So because conversion efficiency For thin crystal is very low. So in this case, we used, I think it was 0.1 millimeter DBO type 1 crystal. So conversion efficiency is very low. But once we add small addition of second color, in this case, fundamental, it was 800 nanometer, second harmonic, it was 400 nanometer. So we absorb so-called enhancement of harmonic generation. So additionally to odd and even orders in our harmonic signal spectra, we can absorb very, very strong enhancement of signal. So there are few explanations why it is happening. So maybe it changing symmetry of our initially isotropical media. So it's not isotropic anymore. So there are some selected directions. But another explanation that once you add a small second harmonic signal, so because high order harmonic generation, it is so-called three-step process. The most important it is last step. So you have strong field ionization, then you have road of electron in electromagnetic field of laser, and the last step when corresponding to emitting of higher order harmonic, it is recombination step. So it is accepted, broadly accepted that by adding small small part of second harmonic, small signal of second harmonic, you improving this last recombination step. So you increase cross section of recommendation, and by this way you increasing overall harmonic. Okay, so we're using two color pump. Okay, let's go to main result. So what so here we can observe really amazing picture. So first of all, so once we combine with so in this case, in C case, we combine radially polarized beam with second harmonic crystal. And as you remember, there are selected orientations for polarization for second harmonic for second one crystal. So actually, we're producing a probe beam consisting of different parts. So this pink blue parts is corresponding to the two color pump. So it means that in this part of beam we have two color pump. So it is 800 plus 400 nanometer. So on the wings of our beam, we have only single color pump. So we can expect generation of harmonics with a very complex waveform. And actually, what we are getting this. So we observe it separation of our wavefront of our harmonic to this different part. So also we can observe that separation is different for odd and even harmonic order. So it can be explained that in case, for example, here, so probably this part and this part of harmonics wavefront is corresponding to these wings of this complex vector beam. So because here there is no enhancement from this no enhancement from this two color pump. So for odd orders, we observe it like enhancement of this component of wavefront. So and this corresponding to this part probably, and so on. So another interesting thing it is when we use the twisted polarization state. So once you combine S plate with linear polarized, but also you rotate S plate, so you can create this twisted direction of polarization. So and you can observe here so how it affects your harmonics wavefront. And here it is like ultimate case when we're using azimuthal polarization, when we use azimuthal polarization. So probably due to the scheme of, because this we absorb, it is after flat field grading. So it is, we can actually absorb only in traverse direction. So here we don't see very clearly structure like in the case C, but it is because it is oriented in this direction, and right now we absorb these parts from the let's say from another orientation. So that's why we absorb only these pink parts here. So it's completely explained and let's continue. So another case, so we also tested, we generated a vortex beam. So again, we used linearly polarized light with different orientations. We used again two color pumps. So we used again DBO type 1 crystal to generate the second harmonic. So, but in this case, distribution of two polar pump is uniform, so it spreads along all beams. And here we generated vortex beams. So just so it is explanation and proves that it is really vortex beam. So the number of high contrast dark regions of stripe after the image shows the average topological charge. So in this case, we had one high contrast dark region in the center of harmonic. So it means that it corresponds to topological charge equal ±1. And direction of inclination of dark stripe establish the sign of topological. So in this case, we generated +1 vortex harmonics using this simple method. Okay, so let me finish. I think my time is finished. So I would like to stress, special acknowledgements to Dr. Arnold Ubelis and Dr. Igors Atvars, and special acknowledgement to Professor Helmut Zakharis and Victor Kachus and Dr. Naresh Reddy. So because together with this team we obtained this the result, and this result will publish it very fastly within a couple months. I think you agree that this not ordinary case in case if you publishing in ACS Photonics. So okay, thank you very much. Thank you for your patience. Any questions?